So we're going to talk today about finding the volume of a solid by rotating about a region. We're going to pin some curves. We'll do some examples. So we'll sketch a region, talk about the solid and the typical disc or washer. Any cat sounds in the back is my cat Tice trying to get some attention. I'm going to start with this problem. It's pretty straightforward. We have y equals x, y equals square root of x, and we're going to rotate that about the line y equals 1. Now again, when we do these curves, often you want to think of the parent function. So I'm thinking of these three in my head immediately. I'm thinking of the line y equals x. I'm thinking of the root function bound this way, y equals square root of x. And finally I'm thinking of just y equals 1, the horizontal line that goes through the value of 1. And I'm trying to picture these all together. One of the first things I do on these curves is try to think of the places where these are going to intersect. And I can quickly see by checking integers in my head that 0 and 1 are the intersection points. And I'm going to marry all three of those together. When I do that, I get this picture right here. Y equals x is the bottom curve. Y equals the square root of x is the top curve from the integrals of 0 to 1 on the x-axis about y equals 1. And since this line is parallel to the x-axis, we're going to have to do the integration with respect to dx. So I immediately write volume equals from the limits of integration a to b, which are going to be 0 and 1, of the cross-sectional area of this shape. And you'll notice here, I blew up the line y equals 1 right here. And I'm going to rotate this region R, which I have shaded down here about this axis. And I'm going to make this volume solid, alright, about y equals 1. And again, this is going to be a washer. This is going to have a shape where it's an outside radius and inside radius. We can see on the picture down here there's an inside radius right here and an outside radius out there. So I immediately, just based on the washer, fill in this. I'm going to go 0 to 1, pi rho squared minus pi ri squared dx. And I have to get variables with respect to x here. Now often this is the most difficult part. We often can graph the lines. We often can make the decision that it's a disc or a washer. But it's calculating the proper ROs and RIs for this rotation. So I blew up that region. And again, for the limits of integration, this is 0, this is 1, here's the x-axis. I don't even show the y-axis. The root function on top, the line on the bottom. And what I show here about the line y equals 1 is that there is an RI, I put that one on here, that goes from y equals 1 to the first function, which is the top function in this case. And I have another line shown here from the x-axis to the same function. Well, I know this distance here is 1 in this case. And I often set it up this way. And I know this height is y, right here. So I have ri plus y has to be 1. Well, y is equivalent to square root of x. And so this time I get 1 minus square root of x. I often have students tell me, well, it's just a number minus the function. Yeah, but it changes. Sometimes it's plus the function. And I always like to make the picture. So I'll show you how I do it on the next one. The next one, if I draw an RO, that would be there. And I draw in my height y, which y is equivalent to x here. I have RO plus y equals 1 again. This time the y is equivalent to x. And I get an RO of 1 minus x. So now I've had RI and RO. And I'm going to take that back to the other graph here for a second. I can just leave that in there and I can roll that down to the bottom of the page. And I can put RI here and I can put RO there. And when I do that, my volume function, and I'm going to pull pi out, factor the pi out, becomes this. Now if you're taking the AP test, often on the non-calculator portion, you can type this right in your calculator and have the integration done for you. Alright? And this would give you the answer if you type this in. Now, often what I do here is I'll take the chance here to do the integration. And I want to be clear, when we do the integration by hand, a binomial squared becomes a trinomial. So this is going to become a trinomial, and this is going to become a trinomial. Now if you want to try this, just pause the video because I'm just going to go through the steps and show you the integration. So the first thing I do is I rewrote the function. I square 1 minus x and get 1 minus 2x plus x squared. I square 1 minus the square root of x, get 1 minus 2 times the square root of x plus x dx. I have some like terms. I have negative 2x and positive x. I have x squared, which I bring down, which was negative 1x. And I have 1 and 1. So I'll combine those before I do the integration. And I end up with this 4-term integration to be done from 0 to 1. So I am a stickler at this when I talk about integration. I always add 1 and divide by the coefficient. So you see here I made this 3 and I divided by 3. I added 1 to 1 here and I divided by 2. This radical is x to the half. When you add 1, it's 3 halves, divide by 3 halves. Finally, even here, you integrate 2, I divide by the 1. I love integrals from 1 to 0, a lot of book examples like that because they're easy to evaluate. I end up by plugging in 1/3 minus 1/2 minus 4/3 plus 2. And you'll notice I also plug in the 0 just to be sure they're all 0. I don't just make the assumption. And when I do the math here, I get the volume of this solid is pi over 2. So coming all the way back, I find the volume of this integral is equal to pi over 2. Again, you got to keep practicing, and I'll post a few more of these today.